Hello guys, welcome on Tesla Eduventures. I was busy in some stuff in making some content for JEE Advanced 2024 and I'll be soon launching that content and this is the video which I'm launching today after a long time. So thanks for your patience and I wish that the first attempt of JEE Mains was well organized by you, and this attempt I think was the easiest attempt. In fact, at least 24th January session was the easiest one for all of the three subjects which I came across by talking to many students and by analyzing the paper. So let us continue the calorimetry part, which was pending after thermal expansion. We have already completed the thermal expansion and we have already uploaded all the videos, and you can see the concept illustration problems of thermal expansion in the previous videos. So now in this video we are going to discuss all of the basic theories of calorimetry. So calorimetry is a branch of thermodynamics which deals with the study of heat exchange between the two substances, which means that under what conditions the two substances exchange the heat and what is the necessary condition for heat flow. This we would study in the calorimetry. So now when there are two substances which are at different temperature and they are in thermal contact with each other, so you know that heat will flow from higher temperature to the lower temperature till they attain the thermal equilibrium. Now this term thermal equilibrium is the condition when the temperature of those two bodies is same which are in thermal equilibrium. And in this condition it is commonly misunderstood that in thermal equilibrium heat doesn't flows. In fact, we know that when the temperature of a gas or a body A is equal to the temperature of body B, so we know that the heat flows in both the directions with equal rate, and therefore the net rate of heat flow is zero in the case of thermal equilibrium. And when any substance is given some heat, it is the heat is utilized in increasing the kinetic energy or the temperature of the material partially, and partially that heat is being utilized in changing the intermolecular separation between any two molecules, or we can say in doing the work against the intermolecular forces. Now we know that intermolecular forces are always attractive in nature, and if we are doing the work done against those intermolecular forces, then obviously that amount of heat is being utilized as the potential energy to change the potential energy, and to change the potential energy means that to change the phase of the element. So when we give some amount of heat to any substance, then that heat is being utilized into two forms. Partially it is utilized in increasing the temperature, and which we can say that the temperature increases when kinetic energy increases, and the remaining amount of that heat is being utilized in doing the work done against intermolecular force attractive forces, and that work done is due to the change of phase of the substance. Now, what is specific heat? You must have observed, you must have heard the term specific heat. So, specific heat is also called as gram specific heat, and it is the amount of heat required by 1 gram of any substance to increase the temperature by 1 degree Celsius or 1 Kelvin. So this is the specific heat and its symbol is S. And let us suppose that for m gram of any substance and for delta T rise in temperature, the heat required would be obviously ms delta T, because for 1 degree Celsius change or 1 Kelvin change, and for 1 gram of that substance, the amount of heat required is S. And for m gram, it would be ms, and for change of temperature of delta T, it would be ms delta T. So S is equal to Q upon m delta T, and the unit of Q is calorie, and unit of m is gram, and delta T is Kelvin. Now what is heat capacity? So heat capacity of any substance is the amount of heat required by that given mass of the substance for 1 degree Celsius or 1 Kelvin rise in temperature. So the basic difference between specific heat and heat capacity is the fact that specific heat is the amount of heat required by 1 gram of that substance, and heat capacity is the amount of heat required by the given mass, whatever the mass is given, that given mass of the substance to show 1 degree Celsius or 1 Kelvin rise in temperature. So this is very evident that we can say that specific heat is only dependent on the material. For example, that the specific heat of 1 gram of copper and the specific heat of 1 gram, in fact 10 grams of copper would be same. But obviously the heat capacity of 1 gram of copper and heat capacity of 10 gram of copper would be different, because heat capacity depends on the amount of substance also. So we know that Q would be equal to H delta T, because H is the amount of heat required by the given amount of that substance to show a temperature rise of 1 Kelvin or 1 degree Celsius. And to show the temperature rise of delta T, the heat required would be H delta T. So H would be equal to Q by delta T, and Q, the unit of Q would be calorie, and delta T is measured in Kelvin. Now we move on the molar specific heat. We know the symbol of molar specific heat is C, and it is defined as the amount of heat required by 1 mole of that substance to show 1 degree Celsius or 1 Kelvin rise in temperature. And for n moles and delta T temperature rise, Q would be equal to NC delta T, and C would be equal to Q upon N delta T. The unit of C would be obviously calorie per mole Kelvin. Now let us analyze that on what factors does this specific heat depends. So we all know that H2O can exist in 3 forms, which is the solid, which is the ice, and the liquid form, which is water, and the gaseous form, which is steam. So the specific heat of H2O in all of these 3 forms is different. So in the solid form, when we call it as ice, then the specific heat of H2O is 0.5 calorie per gram Kelvin. And in the liquid form, when we call it as water, then the specific heat of water is 1 calorie per gram Kelvin. And in the gaseous form, when we call it as steam, then the specific heat is 0.5 calorie per gram Kelvin. This is accurately 0.47, and approximately we can take it as 0.5. Okay, so we can see that the specific heat of a same material depends on the phase in which it exists. So in different phase, the specific heat of the same material can be different. Now for gases, you can see that the specific heat depends on the process through which that gas is going through. So if a gas is going through a isothermal process, then the specific heat is infinity, because T is constant and delta T would be 0 and S would be infinity. Now mathematically S is infinity, but what does it means? That if you have to increase the temperature of this gas, then you have to give the infinite amount of heat, because this gas is going through a process in which its temperature is maintained constant, and any finite amount of heat could not change the temperature of this gas. So to change the temperature of this gas by 1 degree Celsius or 1 Kelvin, we need infinite amount of heat. And in adiabatic process, we know that heat exchange is 0, so Q is 0 and therefore S is 0. So we can say that in adiabatic process the specific heat of the gas is 0, and in polytropic process we would be deriving this formula later on in the part of KTG and thermodynamics, that in polytropic process, in which we can write the equation as PV to the power gamma barabar constant. So we can derive this formula that specific heat in the polytropic process is R upon gamma minus 1 plus R upon 1 minus R. This is polytropic constant, and this is adiabatic constant Cp by Cv. Now let us talk about the latent heat. We have already discussed that the heat given to any substance is utilized in two ways. The first one is to increase the temperature and hence to increase the kinetic energy of the substance, and the other one is to change the phase of that substance, or we can say that in doing the work done against intermolecular forces. So now we are discussing the later one, in which we are changing the phase of the substance. So you should always remember that whenever phase changes, then the temperature of the substance remains constant, obviously, because all of the heat is being utilized in changing the phase only. And whenever the temperature changes, then phase does not changes. So we can easily analyze this statement by the fact that when ice melts, then obviously its temperature is constant 0 degrees Celsius, but all the heat which is given to the ice is being utilized in increasing its in fact melting it. And when water boils, we know that its temperature becomes constant at boiling point, which is 100 degrees Celsius for water, and the phase of that amount of liquid or water is changing from liquid to gaseous phase. So when phase changes, temperature remains constant, and when temperature changes, phase does not changes. Okay. Now we are talking about the latent heat. So latent heat is the heat involved when the phase changes of that substance, and the amount of that substance should be 1 gram. So the heat involved in change of phase of 1 gram of any substance is called as the latent heat of that substance. And for m gram of that substance, heat involved would be m into L. Now why I am saying the heat involved? Because when ice melts, let's suppose when 1 gram of ice melts, then it absorbs 80 calorie per gram for melting, and when water freezes, then it releases 80 calorie per gram to freeze. Okay, so for both of them, we can say that heat involved per gram is called as latent heat. Now latent heat is of two types. The first one is the latent heat of fusion, and the second one is the latent heat of vaporization. Now we know that when the phase changes from solid to liquid or from liquid to solid, then this process is called as fusion, and the heat involved in converting 1 gram of any solid into liquid or 1 gram of any liquid into solid is called as latent heat of fusion, and it is 80 calorie per gram, which I have already discussed in the previous example. And latent heat of vaporization is the heat involved in converting 1 gram of liquid into vapor or 1 gram of vapor into liquid, and its value is 540 calorie per gram. Okay, so this what it is means. What does it means is the fact that when we boil the water, then 1 gram of water requires a heat of 540 calorie for boiling and to convert into steam, and when steam condenses back into liquid or water, then 1 gram of steam releases out a heat of 540 calorie per gram. We know that obviously when ice melts, when ice falls, obviously the fall of ice on the earth, and the point when that falled ice melts, then that at the time of melting of ice requires per gram 80 calorie. And when the so much huge amount of ice melts, then obviously if we calculate the total amount of heat required by that ice to melt is m into 80. So such a huge amount of heat which is melting, such a huge amount of ice which is melting on the surface of earth requires a huge amount of heat which is absorbed by the ice from atmosphere, and therefore the temperature of the atmosphere falls. So we can say that when that ice melts, then the temperature of atmosphere falls to a greater extent, and we can see that when the ice melts at hill stations, then there is a quite low temperatures which are recorded at the hill stations. Now it is also said that it is more dangerous to get burned from 100 degree Celsius steam as compared to the 100 degree Celsius of water, due to the fact that when you would be burned by 100 degrees Celsius of water, then it would only require, let's suppose our skin temperature is 80 degrees Celsius and we are getting burned by 100 degrees Celsius of water. So final temperature of the water would become 80 and the heat given by the water would be ms delta T, and delta T would be 80. But when we would be burned by 100 degrees Celsius of steam, then what would happen, that that steam would first convert into 100 degrees Celsius of water, and it would release out 540 calorie additional heat per gram in conversion, and then that water will move to 80 degrees Celsius from 100 degrees Celsius, giving the same amount of heat which was given in the previous case. So we are receiving additional 540 calorie per gram by that steam when it is converting back into the water, and this is the fact that our skin would receive the more heat by the steam at 100 degrees Celsius, and it would be burned, and there would be severe burns in the case of steam. Now, the water equivalent is also the quantity which is used for calorimeters. The calorimeter is a device, we can say that calorimeter is a copper device or copper vessel which is used to stir, or which is used to mix the two liquids or two different substances which are at different temperatures. So water equivalent of a substance is the amount of water that would have same heat capacity as that of that substance. I know this definition is not suitable for understanding the water equivalent, so I would explain this water equivalent with a easier example. Let us suppose that I have taken m gram of any substance whose specific heat is S, and I gave that substance a total amount of Q heat. So Q was equal to ms delta T, and delta T was the temperature rise that was shown by that substance by receiving amount of Q heat. Okay, so now I want to know that what amount of water should I take so that by giving the same amount of heat, it also shows the same temperature rise delta T as shown by that substance. So let us suppose I have taken a W amount of water which is being given the same amount of heat, and it also showed the same temperature rise by that substance. This means that this W is the water equivalent of this substance, and when we equate these two, then delta T is cancelled out and W is equal to ms. Now it is a deception that some people say that the unit of W is m into S, so the unit of S is calorie per gram Kelvin, and unit of m is gram. So some people say that unit of W is calorie per Kelvin. This is wrong, because here you can see when we are taking this formula, then the specific heat of water is 1. So we have written 1 here, and the unit of 1 would be cancelled out with the unit of s, and therefore the unit of w would be only equal to the unit of m. So the unit of w is equal to the grams. Okay, now we move further on. Now let us discuss about the melting. So as you all know that melting is a process of conversion of solid into liquid into at constant temperature. So the best example of melting is obviously the melting of ice, and when ice melts then the temperature remains constant at 0 degree Celsius. So in most of the cases the pressure, the ambient pressure also remains constant throughout the melting, and we assume that in the change of phase, for example in the case of melting of ice, the pressure of surrounding remains constant. Now evaporation. So evaporation is the conversion of liquid into vapors at all the temperatures, and evaporation can occur on the surface only. Obviously let us see that when there is a container which is full of water, then evaporation will be occurring at the surface of the water and not on the deeper sides. But we know that boiling occurs in the complete water. When water boils, then at boiling point, which is 100 degrees Celsius, the boiling occurs in the complete water, not just only on the surface. Now rate of evaporation increases with the temperature. This is due to the fact that molecules have greater kinetic energy at higher temperatures, so they tend to run here and there, and in this process they are more probable to break their bonds and get evaporated. And the smaller is the boiling point of the liquid, more rapid would be the evaporation. Obviously if a liquid have a smaller boiling point, then it has a greater tendency to evaporate faster. Now when humidity is small, then the evaporation is more rapid, obviously because at small humidity the amount of vapor present in the atmosphere or the surrounding is small, and hence the pressure of those vapors is small, and there is enough amount of space left for additional vapors to be accommodated into that surrounding or atmosphere. Now rate of evaporation increases with the decrease in ambient pressure, and therefore evaporation is highly rapid in vacuum. Obviously we know that due to the air pressure, the molecules are restricted to break their bonds in the liquid, and they are being restricted to evaporate. But if the pressure of the surrounding is small, then there is no force which is restricting those molecules to come out and to break their bonds and to evaporate. Hence evaporation would be more in the low pressure. And you can also see that evaporation would be highly rapid in vacuum, because there is no restricting force which is restricting the atoms or molecules to get evaporate. You must have observed that when we mop the floor, then we usually we switch on the fans, and due to those fans the mopped floor gets dry quickly. You have seen this phenomena on in your home on day-to-day basis. So this is also due to the fact that when we mop the floor and we switch on the fans, then the air velocity above the mopped floor becomes high, and due to high air velocity the pressure of air becomes low, and due to low pressure the evaporation rate becomes higher. So water evaporates with much higher rate. Now heat of evaporation is the heat required to change a unit mass of liquid into vapors at a given temperature. and heat of evaporation is obviously temperature dependent. So the different amounts of heat would be required to evaporate a unit mass at different temperatures. So heat of evaporation is a temperature dependent term. Now sublimation. Sublimation is the direct conversion of solid into vapors, and we have seen, obviously we have seen the camphor at our home to sublimate, and the heat of sublimation is the amount of heat required by a unit mass of a solid to directly convert into vapors at a given temperature. And obviously heat of sublimation is also temperature dependent, so at different temperatures the heat of sublimation would be different. Camphor and ammonium chlorides sublimates, obviously sublimates naturally, and if we heat them, then the sublimation rate becomes higher. And a block of ice also sublimates on the surface of moon due to the fact that there is very low pressure on the surface of moon. Therefore the block of ice directly gets converted into vapors on the moon surface. Now condensation is the process of conversion of gas or vapor state into liquid, and this process is just reverse process of evaporation. And the materials which can condense can also be converted back into gas or vapors on heating, obviously. So we often see the white fumes around the ice cube when we take it out from a refrigerator. So that white fumes is the condensed humidity that is condensed in the air due to the contact of a very low temperature ice, and that condensed humidity tries to block the light. That is why we observe that portion as translucent. So we call it as white fumes. Now phase of a substance. So phase of a substance is its form in which is homogeneous and physically distinct. We can obviously distinct the phases, and which is mechanically separable from the other forms of that substance. Obviously we know that the solid form, liquid form and gaseous form is physically distinct, and we can mechanically separate these three forms. So these are called as phase. And the phase diagram is the graph plotted between the pressure, which is represented on y-axis, and the temperature, which is represented on x-axis. Now what are the characteristics of a phase diagram? So different phases can be shown on a phase diagram. A region bounded between any two curve is representing a single phase of a substance, and a curve represents the equilibrium between two phases lying on the either side of that curve. I would be showing you a practical phase diagram for water in the next page, so just wait for it. And a common point on the phase diagram represents the equilibrium among the three phases. Now the phase diagram helps us to determine the conditions under which different phases can be in equilibrium. For example, you can see this phase diagram. In this phase diagram, it is plotted for water, and on the y-axis pressure is taken in kilopascals, and on the x-axis temperature is taken in degrees Celsius. So this is a phase diagram of water, and these are three curves. Now this curve is a straight line, and this region is the solid region of water, which is ice, and the region trapped between this curve and this curve is the liquid form of water, which is water, obviously. And the region trapped between this curve and x-axis is the vapor form of the water, which is steam. So we can say that this is the common point which is common for all of these three regions. So we can say that at this point, which is at zero point 0.6 kilopascals and 0.01 degree Celsius of temperature, the water has all of its three states in equilibrium, which means that water exists in solid, liquid and vapor form at this pressure and temperature. And obviously this curve represents all of those points at which water is in equilibrium in solid and liquid phase, which means that at all the pressures lying on this line and at all the temperatures lying on this line, the water would be coexisting as a solid, which is ice, and liquid. And the same thing is for this curve, that at all the pressures and at all the temperatures on this curve, water would be coexisting in the form of liquid and vapor. And similarly, at all the points on this curve, water would be coexisting in form of solid and vapor. Okay, and we know obviously that the normal melting point is 0 degree Celsius, and the pressure at that melting point is 1.01 into 10 raised to power 5 pascals, which is this one. So this is normal melting point and this is normal boiling point, and this line, this curve is called as sublimation curve, this line is called as fusion curve, and it is called as vaporization curve. So this was the complete theoretical part of this calorimetry, and in the next video I would be demonstrating the most important questions of this calorimetry, which are ice water mixture problems and some more problems in the next video. Thank you.